Today we will be doing alternating current. Alternating current is current which varies sinusoidally with time. So if you have current which varies with time according to a relation I equal to I0 sine omega t plus phi, then this is known as alternating current. So the graph of alternating current would look somewhat like this. This is current and this is time. Now all the terms pertaining to a sinusoidal equation, for example time period, will be applicable here also. Say for example time period, you know the formula is 2 pi by omega, so that formula will be applicable here also. Then I0 is called current amplitude. So current amplitude is I0. So the terms which are applicable to any sinusoidal equation in general will also be applicable here. Phi, if you recall, is called the phase constant. So these are terms which you are already familiar with, and these terms are also applicable in case of alternating current. Now one of the things which physicists were very curious to understand is how to use current for calculations such as energy consumption, power dissipation, etc. So this was a great concern to the physicists. Now they found that if you take average current in one time period, which is of course given by integral 0 to time period I dt, so divided by t, so this will become so the answer will come 0. So the average current 0 to time period I dt divided by t, so the answer comes to 0. So the average current in one time period is 0. So average current doesn't seem to be a very useful entity in our calculations. And precisely why is it coming to 0? Because you will appreciate that one time period consists of a positive half cycle and a negative half cycle, and the total of these two will always give a 0. So then they decided to take the average of current square, because the reason why average current is coming to 0 is because the half cycles are of opposite sign. So then they decided to take the average of current square. That means 0 to t I square dt divided by t. So this comes to 0 to t I0 square sine square omega t plus phi dt divided by t, and after integration the answer comes to I0 square by 2. So the average of I square turns out to be equal to I0 square by 2. Now suppose if I were to do the square root of the average of I square, the answer would be I0 by root 2. So this square root of the average of I square is known as IRMS, because root means square. You are first squaring the current, then taking the mean, and then finally you are doing square root. So this I0 by root 2 is known as IRMS, or the RMS current in the circuit. But is it a useful entity? Can we use IRMS in our calculations? Well, the answer is yes. Let's see how. Suppose we wish to find thermal energy in one time period. So this is coming to 0 to t I square r dt. So that is coming 0 to t I square sine square omega t plus phi dt. So after simplification, it was found that it is coming I square RMS into RT. So very interesting thing, that the thermal energy in one time period, 0 to capital T I square R dt, after simplification it is coming equal to I square RMS into RT. So this is a very important result, because it tells us that for the purpose of energy calculation, we can treat IRMS as the average current in one time period. So this has greatly simplified the analysis of AC current, because now we are able to take a value IRMS and use it as an average value of the current for important computations like energy. In fact, IRMS is also called virtual current, because if you plug a ammeter into the circuit, you will not be able to get this reading. So IRMS is a hypothetical value which is merely taken as an average current in a time period, but if you actually use an ammeter in a circuit, you will not get this reading. You will get all possible readings, but IRMS is not the constant current recorded in the circuit. So it is also known as virtual current. Now, just like I is equal to I0 sine omega t plus phi, similarly we can have V equal to V0 sine omega t plus phi. So V0 is the peak voltage, and Vrms is equal to V0 by root 2, just like IRMS is I0 by root 2. Now in our country, in India, in domestic supply, Vrms is 220 volt. So you know that in our country, the domestic household supply is maintained at 220 volt, and therefore the peak current will be 220 into root 2, that is 311 volt. Now we will discuss some very common AC circuits. The first one is circuit with only resistor. Suppose there is a circuit in which the voltage supply is E0 sine omega t, the current is I, there is only a resistor. So you can say by using Kirchhoff's law that E0 sine omega t is equal to IR. I is equal to E0 by R sine omega t. So I is equal to I0 sine omega t. So if you have a AC circuit with only a resistor, then E0 sine omega t is IR. So I is E0 by R sine omega t. So I is equal to I0 sine omega t. Then we come to circuit with only capacitor. Suppose there is a circuit in which you only have a capacitor. Supply voltage as usual is E0 sine omega t, current is I. First of all, current is dq by dt. If you use Kirchhoff's law, E0 sine omega t is q by c. So Q is equal to CE0 sine omega t. So I is equal to dq by dt. That is CE0 omega into cos omega t. So now we can say that I is equal to I0 cos omega t, where I0 is CE0 omega. That means we can write I0 is E0 by 1 by omega c. Now E0 has unit of voltage and I0 is unit of current. So this will be having the units of resistance, that means ohms, and in fact it is called the capacitive reactance of the circuit. So the capacitive reactance of the circuit is given by Xc is equal to 1 by omega c. Now the current expression which we got, we can also write it like this: I0 sine omega t plus pi by 2. We can write it in this format. Now if you try to graph the current and the voltage together, you will see that the voltage graph will be this and the dotted line will be the current graph. So we say that current leads EMF by pi by 2. So you will notice that Since I is equal to I0 sine omega t plus pi by 2, you will notice that if you graph voltage and current together, then this solid line is the voltage graph and dashed line is the current graph, and we can say that the current leads the EMF by pi by 2. So this is AC circuit with only capacitor. Next we come to AC circuit with only inductor. So if you have an AC circuit with only inductor, and if you decide to apply Kirchhoff's law on this circuit, E0 sin omega t minus L di by dt is 0. So di by dt is E0 by L sin omega t. If you integrate both sides, I equal to minus E0 by omega L cos omega t. So I is E0 by L sin omega t minus pi by 2. This E0 by omega L, we can call it the peak current or current amplitude, and once again you will notice that E0 has the same dimensions as voltage. I0 unit is current, so XL, the unit will be the same as resistance, that is ohms. So XL is called the inductive reactance of the circuit, right? And one more thing is, in order to find the value of the constant C, we can use the fact that average I in one time period is 0, and average of cos omega t in one time period is also 0. So average of I in one time period is 0 and average of cos omega t in one time period is also 0. So we are getting C equal to 0. So this is the relation for current in the circuit. Now if you try to graph the voltage and the current together, this is how it will look. If you try to graph the voltage and the current together, this is the voltage graph and this dashed line is the current graph. If you graph them together, it will look like this, and you can see that current lags behind EMF by pi by 2. So current lags behind EMF by pi by 2. So these are the three simple circuits, that is current circuit with only resistor, circuit with only capacitor, and circuit with only inductor. Now we come to combination circuits. For example, let us say you have a circuit with capacitor and resistor, CR circuit. Now what happens is that if you try to apply Kirchhoff's law directly for a CR circuit, it will fail, which means that if you try to sum up all the voltage drops arithmetically, the total will not come to zero. The reason is, as we have learnt a few minutes back, that whenever you have a capacitor in a circuit, then the current will lead the supply voltage by pi by 2, and we have also learned that in case of a circuit with a resistor, the current and the voltage will be in the same phase. Effectively speaking, the voltage drop across the capacitor is pi by 2 ahead of the voltage drop on the resistor. So the scientists came up with a very interesting concept called phasor diagram. So phasor, combination of phase and vector, but we cannot truly call all the quantities discussed vectors because this chapter deals only with scalar quantities. So the phase of the current across the resistor is represented by this arrow. The phase of the current across the capacitor is represented by this arrow. And you can see that the angle is 90 between them. So the phase of the resultant of these two will be represented by the diagonal of the rectangle, and in fact Z is equal to root over R square plus 1 by omega C square is called the impedance of the circuit. So Z is equal to root over R square plus 1 by omega C square is called the impedance of the circuit, and this phase angle phi can be found out by using tan phi is equal to 1 by omega CR. So we will now get a relation like this. I is equal to E0 by Z sine omega t plus phi. So this is the resultant current for a CR circuit, and you can see that the circuit impedance Z is below the E0 and the phase angle phi is over here. So this is the first type of combination circuit, that is CR circuit. Next, number 5, let us discuss LR circuit. In a LR circuit also the issue remains that how do we consider the phase? So you know that the phase of the current across the resistor, if it is represented by this arrow, then phase of the current across the inductor will be represented by this one. And Z is the impedance of the circuit. So Z is equal to root over R square plus omega square L square. And the phase angle phi can be found by the equation tan phi equal to omega L by R. So I is E0 by Z sine omega t minus phi. So this is the resultant current in a LR circuit. Next we come to LCR circuit. In a LCR circuit, the inductor L, resistor R, capacitor C connected in series. Now, in such a circuit, one of the two has to be greater, the reactance of the capacitor or reactance of the inductor. So if the reactance of the capacitor is greater, then the phasor will look like this. So Z is equal to root over R square plus 1 by omega C minus omega L whole square. Tan phi is 1 by omega C minus omega L by R. So I is equal to E0 by Z sine omega t plus phi. This is the value of I. Now let us say that in a particular circuit L, R, C are constants, but we are in a position to manipulate the frequency of the AC supply. Suppose we can manipulate omega. So in that case we can now discuss under what circumstances the current amplitude will be maximum. Now you can see that this is the expression for the current amplitude. So if the current amplitude has to be maximum, then this term has to be 0. If you equate it to 0, the corresponding value of omega is known as resonance angular frequency. And the corresponding value of frequency is called resonant frequency of the circuit. So the resonant frequency of the circuit will be 1 by 2 pi root LC. Now if you try to draw the graph of peak current versus angular frequency, this is how the graph will look. So this is the graph of peak current versus angular frequency, and you can see that corresponding to omega naught, the peak current is maximum. Now let us consider the value, or rather let us consider the values of omega for which the peak current is I0 by root 2. So in fact it's probably better if we call this as Im and this as Im by root 2. So you can see that this is the graph of I0 versus omega, and Im is the maximum value of I0, and this is Im by root 2. Now in this particular circuit, if we use the relation E0 by R root 2 so as I told you that Im by root 2 will correspond to two values of omega, omega 1 and omega 2. So if we apply all these conditions mathematically, we will get E0 by R root 2 is E0 by root over R square plus omega 1L minus 1 by omega 1C whole square. So on squaring both sides, we will get 2R square equal to R square plus omega 1L minus 1 by omega 1C. So this is the expression which we are getting for omega 1 in terms of R. Now using this expression, we will now write omega 1 as omega 0 plus delta omega So we will get omega 0 plus delta omega into L minus 1 by omega 0 plus delta omega into C is equal to R. Now you take omega 0 into L common. So omega 0 L into 1 plus delta omega by omega 0 minus 1 by omega 0 C into 1 plus delta omega by omega 0 equal to R. Now you know that resonating frequency omega 0 square is 1 by LC. So you can write omega 0 C is 1 by omega 0 L. And using binomial theorem and considering that delta omega will be very very small compared to omega 0, we can write like this. Now if you open the brackets, you will get 2 omega 0 L into delta omega by omega 0 is equal to R. So this will give you delta omega is equal to R by 2L. In such a circuit, there is a term called Q. Q is called quality factor. So quality factor is given by omega 0 by twice delta omega, and you will see by using this relation that its value is omega 0 L by R. Now why is quality factor a very important term? You see, in this circuit, if delta omega is very very small, then quality factor will be very high. If delta omega is very large, quality factor will be very low. So if delta omega is very low, that means the resonance is sharp. So just to give you an idea what I mean by sharp resonance is if I have the I0 versus omega graph like this, then the resonance is not sharp, right? And if the graph was like this, the one which I have originally drawn, then the resonance is comparatively sharper. So you can get a better resonance with a higher quality factor. And one more thing is that twice delta omega is called bandwidth. So now we can say that sharp resonance corresponds to low bandwidth. So calling the resonance sharp is equivalent to calling the bandwidth low. Now we come to power consumption in AC circuits. Suppose you have a AC supply. So work done by the supply in sending current in the circuit, dW will be voltage into current into dt. So if you substitute the values, this is what you will get: E0 sine omega t into I0 sine omega t plus phi into dt. So the total work done is in one time period, the total work done is E0 I0 sine omega t into sine omega t plus phi integration from 0 to t. After completing the integration, you will find that the answer is half E0 I0 capital T into cos phi. So E0 by root 2 I0 by root 2 into cos phi. So that means the power consumed is ERMS into IRMS. Now the term cos phi is known as power factor. If you have a purely reactive circuit, that means it has only capacitor or only inductor, then phi will be either pi by 2 or minus pi by 2. So cos phi will be 0. So if you have a circuit which is purely reactive, that means phi is either pi by 2 or minus pi by 2, then cos phi will be 0. So this particular attribute of a purely reactive circuit, or this attribute of inductors and capacitors to give zero power consumption, has a lot of practical applications. So we will now have a look at one such practical application. So we will discuss one application that is known as choke coil. Suppose you have a circuit in which the supply voltage is V0 sin omega t, and let us say that in this circuit you are using a tube light whose resistance is R. The problem is that tube lights cannot function at 220 volt supply voltage. Their operating voltage is much less. So to reduce the voltage, we attach an inductor in series. So if you attach the inductor, the impedance of the circuit becomes root over R square plus omega square L square. Now I0 will be V0 by inductance. IRMS will be I0 by root 2. So this will be the formula for IRMS. So what will be the RMS voltage delivered across the tube light? The RMS voltage delivered across the tube light will be R by root over R square plus omega square L square into VRMS, and clearly this is less than the supply voltage of VRMS. So by attaching an inductor in series with the tube light, we are able to ensure that the voltage delivered across the tube light is less than the RMS voltage of 220 volts. Secondly, an inductor gives zero power consumption, so it is a better alternative to applying a resistor in series. So this is one practical application of zero power consumption of an inductor. Next we will come to transformer. In a transformer, there is a primary circuit and a secondary circuit. And both the circuits are associated by a soft iron core. This is a soft iron core. So in the primary circuit you will have several turns. So suppose the number of turns of the conducting wire is Np. There will be a supply voltage, suppose E1, and due to this there will be a current, that is I1. E1 is an AC supply voltage. Similarly, on the secondary side of the circuit, the conductor will have a certain number of turns, let us call that as Ns. Now what will happen is that since this is an AC supply, when the current is passing through these turns, then the current is alternating current. So the magnetic flux linked with these coils will keep changing, and due to the flux change, if you apply Kirchhoff's law, for the primary circuit, you will get E1 minus N1 into d phi by dt is 0. So this is the result of applying Kirchhoff's law on the primary circuit. Now thanks to the nature of soft iron, whatever flux change occurs in the primary will be transmitted to the secondary, and by Lenz's law, or you could say by the concept of mutual induction, the EMF induced in the secondary will be 180 degree or completely out of phase with respect to the EMF of the primary. So the EMF induced in the secondary is given by minus N2 into d phi by dt. You will notice that in both of them the rate of change of flux is taken to be the same. That is thanks to the transformer. So now we will get E2 is N2 by N1 into E1. So this is the relation between the voltage delivered across the primary and the secondary. Now the entire process is assumed to be without any power loss. So E1 into I1 is the power in the primary circuit, and E2 into I2 is the power in the secondary circuit. So if you neglect loss of energy, you can say that E1 I1 is equal to E2 I2. Now if N2 is greater than N1, so we can say that E2 is greater than E1. So this is called a step-up transformer. In a step-up transformer, the output voltage is greater than the input voltage. But if E2 is greater than E1, we can say that I1 is greater than I2. So that means the primary coil is thicker than the secondary coil. So in any step-up transformer, the primary coil is thicker than the secondary coil. Now if N1 is greater than N2, then E1 is greater than E2. This is called a step down transformer. So I2 is greater than I1. So that means the secondary coil is thicker. So in a step-up transformer, the primary coil is thicker, and in a step-down transformer, the secondary coil is thicker. Next we come to LC oscillations. Suppose you have a circuit with a capacitor and an inductor. Capacitor is fully charged. So the capacitor will send a current I into the circuit. If you apply Kirchhoff's law, you will get Q by C minus L di by dt is equal to 0. Now remember, the capacitor is discharging current, so I will be minus dq by dt. If you combine these two equations, then d2q by dt square plus q by lc is equal to 0. Now this is a equation which is a second order linear equation, and you will see that it is actually similar to the equation of a simple harmonic oscillator. So the solution of such an equation is given by Q equal to Qm cos omega t plus phi, where Qm is the charge amplitude. Now, as I said right at the beginning, the capacitor is fully charged, so when time is 0, Q is Qm. So this gives phi equal to 0. And one more thing is, you know that omega 0 is equal to 1 by root LC. So we can now write the equation as Q equal to Qm cos omega 0 t. So if you differentiate both sides, I will be Im into sine omega 0 t. So Im is equal to Q0 into Qm, omega 0 into Qm. So these are the details of a LC oscillator circuit. Now let us analyze the energy changes. Right at the beginning, the capacitor is fully charged, and this is the inductor, the circuit is open. So the charge of the capacitor will be 0. The energy of the inductor will be 0 and the energy of the capacitor will be Qm square by 2C. So let this be the situation at time 0. Now suppose you consider a time between 0 to t by 4 . So this is how the current in the circuit will appear. Now let us say you consider the time t by 4. So when the time becomes t by 4, the magnetic energy of the inductor becomes half Li m square and energy of the capacitor becomes 0. Again, let us consider a situation when time is between t by 4 and t by 2. Now this time what will happen is the inductor will send current into the circuit and the plates of the capacitor will be charged in the manner opposite to the initial charge. And finally, at time t by 2, the energy of the capacitor will again become Qm square by 2C and the energy of the inductor will again become 0. So the total energy will remain constant. Sometimes it will be purely electrostatic energy, sometimes it will be purely magnetic energy, and at some other times like these two, it will be a combination of electrostatic and magnetic energy, but the total energy will be a constant. So this completes LC oscillations, and it also brings us to an end of the chapter alternating current.